Swayam Prabha. Digital India. Educated India.
Hello. So, we solved a problem which is the bar optimization problem, that is stiffest bar for given amount of material, and we also discussed this optimality criteria method and looked at the MATLAB code. Now, we will go back to calculus of variations once again, because there are a few things that we need to learn there, few more things, and that is to recall. Let us write down the problem. So far what we have discussed in calculus of variations is minimize a functional j with respect to a function y of x or many, let us say we take one function, okay, or a vector of function, let us take y bar, y1, y2, y3, yn, and we have an integral in terms of only one variable which is x, x1 to x2. We had integrand that depends on y1, y2 and any number of its n functions, and then the first derivative, second derivative and so forth up to whatever you want, right. So, this is y1, y2 double derivative and so forth, but our independent variable which is this was still x, that is we are doing one dimensional problems. Now, what we will do is we will graduate to more than one dimension, because most of the problems that we encounter in mechanics are not one dimensional. Bars and beams are, but plates are not, membranes are not, and general 3D structures of course are 3 dimensional or 2D structures, right. So, we want to go to more than one dimension, in which case all our functions will not be a function of x alone, they will be functions of x and y, okay, that is the difference. In terms of the constraints, functional type constraints and function type constraints, global and local constraints, they will be the same. All the change that will occur now will be in terms of the number of independent variables, okay. So far it is only x that is variable. Now our functional will have x1, x2, we will make now y as our independent variable, okay. Instead of making y as a function of x, we will make y as an independent variable and make z as a function of x and y. It is a 2D problem now, okay. And our integrand then will be a function of z, and its first derivative, when I say first derivative now, there are two first derivatives which are partial, dou z by dou x and then dou z by dou y, and then we write dx dy. Our domain in that case was just a straight line region with one variable. Now it is a 2 dimensional domain. So, what we have here, okay, so this particular thing I can also write this as over some area, and then I write my integrand f z dou z by dou x dou z by dou y, I will write dA. So, this is dA and this region is A. So, if I take x and y, let us say this is x and this is y, some arbitrary region, okay, that is our A. Over that we have a function that is defined. If I say z axis going perpendicular to this xy plane, and that zxy surface whose projection is this area, that domain, okay, this is our domain for the function zxy. So, we need to find a function of two variables such that this functional is minimized. Okay. That is a problem we consider, and later 2 variables can become 3 variables also. Mechanics, from the mechanics perspective, we can also think about physical problems that look like this. If we imagine, let us say we have a plate, okay, let us say its plate is clamped here, maybe in all edges, let us say plate is clamped. Okay. Now, at every point x and y here, there will be deformation. So, there will be, first of all there will be some loading on the plate, and the plate is going to deform, right. So, plate may deform something like this, depending on what kind of loading that you have put. Now, this deformation is W, which is a function of x and y. For a beam it is only x. Now, for W, which is a function of x and y, that is a 2D problem. Okay. So, here also the plate will be minimizing its potential energy. So, we can write minimize with respect to W, which is a function of x and y, this is W, we minimize potential energy. If I do that, then I will be getting, this is W. If I solve this, I should get the plate equation. You are most likely familiar with the beam equation and how it is derived and so forth. Now, we can also do plate equation if we know how to write the potential energy and minimize it with respect to W x y, which is a function of 2 independent variables x and y. That is a problem we will consider now. Okay. So, let us start by writing out the problem from first principles, like we had done when we had only y of x. Now, we have z x plus y j integral over some area. I will not write x1 to x2, y1 to y2, that is good for rectangular domains. But if I write area A like this, it can be any arbitrary domain such as the one we have shown here. Okay. So, I minimize this and I can write my integrand first in terms of z, and I will use this notation because we will have lots of things to write. The notation that we are using from now onwards, when I write z sub x, it means dou z by dou x, likewise z sub y equal to dou z by dou y, and here we have to complete the dA. This is the problem we want to solve. Now, when I take variation of j with respect to z, that is our variable z x y, okay, and we have to equate to 0, what we get, if you remember the definition of Gaussian variation, where we have z plus epsilon h. Now, earlier h was only a function of x, now h will be a function of x and y. That h can also be called delta z, because that is a variation of z. Okay. Then we take derivative, normal derivative with respect to epsilon, and then substitute epsilon equal to 0. If we do all that, what we get will be this integral dou f by dou z times delta z. Okay. The delta z, earlier we were writing it as h. Okay. Now, I am using delta z to clearly indicate that it is a variation of z. So, we have a surface, we perturb the surface a little bit, that perturbation is h. That is how we find something is local minimum or not, right. So, we perturb the function and then see whether objective function increases or not. If it increases, then what we have is actually a local minimum. That is our trick. So, we need to consider variation, and then since it also depends on zx, meaning dou z by dou x, we have to do dou f by dou z sub x, meaning dou f by dou z by dou x. Okay. That means wherever f has zx terms, that is what we differentiate into perturbation of zx. Okay. That is dou delta z by dou x, and we will also have dou f by dou z y delta z y, and then we will have dA as usual. This should be equal to 0, that is what we have. Okay. Now, if you remember, when we had the first derivative y prime or dy by dx, in order to derive the Euler-Lagrange equation, we had done integration by parts. In the case of 2 dimensions, means we have 2 variables x and y, we have to use something that is equivalent to integration by parts in 2 dimensions, that is a Green's theorem. Okay. Before we do that, our objective, if you recall, is to convert these delta z sub x, delta z sub y into delta z, because then we know that delta z is arbitrary, and then we can say that using fundamental lemma of calculus of variations, what multiplies that is equal to 0, we get the necessary condition in the form of a differential equation. So, what we do here, in order to convert these things into delta z, we use a small trick. Okay. It is just a very small trick, in fact trick is probably not the right word, but if you do not know how to proceed, somebody tells you, then they have given you a trick. So, what we do is we write dou f by dou z x delta z x as dou by dou x of f and delta z. Actually, what we will do is we will write dou f by dou z x into delta z. Now, if I were to use product rule and expand it, I will get this one, but I will also get what I will subtract now, because it should be on the other side. This will be dou by dou x of dou f by dou z x into delta z. Okay. So, notice that if this particular thing is expanded, I get this term plus this term, and I have gotten it to the right hand side. In other words, I will be replacing this thing, which is what we have, with this and that. Okay. We throw this away, instead of that what is equal, these two things we substitute. The reason we are doing is, whatever delta z sub x that we had, now that has been taken out. Okay. So, that is what we are trying to do. So, we are taking dou by dou x of this, then that gives us this, all right. That is our aim. It is like replacing delta z sub x with something that involves only delta z. Similarly, for this other term, right. So, that one we will replace with dou by dou y of dou f by dou z y delta z minus dou by dou y of dou f by dou z y delta z. Okay. With this, we can rewrite our necessary condition in this manner. So, the delta z variation with respect to the z function that we have equal to 0 will now have integral a over the domain A, dou f by dou z, that is this term that remains the same. So, we have dou f by dou z into delta z, and then I will take what I am replacing, this and this. I will take the one that has delta z and write this separately. So, this will be minus dou by dou x into dou f by dou z x delta z, and then this also minus dou by dou y into dou f by dou z y times delta z. So, all these have delta z. Let us put it together. On the other part, that is we have this quantity and this quantity. I will write separately. Okay. So, what I have there is dou by dou x of dou f by dou z x delta z plus dou by dou y of dou f by dou z y delta z. So, this will be dA here, likewise we will have dA there. Okay. Both are still integrated over the 2-dimensional domain, arbitrary domain, but the first term if you see these are all delta z. Okay. So, I will write that implies, of course, this whole thing is equal to 0, that is our necessary condition. So, I got is A into dou f by dou z minus dou by dou x of dou f by dou z x minus dou by dou y of dou f by dou z y, whole thing multiplied by z. Okay, that is first part. Second part is dou by dou x of dou f by dou z x delta z plus dou by dou y of dou f by dou z y delta z times delta z dA. Oh, sorry, this delta z is not there. Okay, this is simply dA is equal to 0. So, we have two parts and this is arbitrary, delta is arbitrary, which is clearly outside. So, what multiplies according to fundamental lemma must be equal to 0. We have two parts, this differential equation part and the boundary condition part. Let us remember, this is the differential equation part of the necessary condition, whereas this is the boundary condition part. Both parts are equal to 0. We make individual ones equal to 0 because the reason that we had given, somehow with some delta z you make it work so that individual parts are not 0, but together they are 0, but that is not enough because delta z is arbitrary, it should work for anything. That is why we make it individually 0. When this is 0, since delta z is the variation and hence it is arbitrary, we get the differential equation which is dou f by dou z minus dou by dou x of dou f by dou z minus dou by dou y of dou f by dou z y, that is equal to 0. Okay. So, that is our differential equation. Okay. In fact, if you recall, this is actually Euler-Lagrange equation, there are two independent variables. If you recall, it was dou f by dou y minus d by dx of dou f by dou y prime, that is exactly what we have, only thing is with partial derivatives. Okay. For the boundary condition part is little tricky. So, because there is no delta z jetting out here, it is inside, delta z is inside. To get it outside, we use Green's theorem. Differential equation part, Euler-Lagrange equation should be clear to you. Okay. Whatever was total derivative becomes partial derivative, that is all. Okay. There is nothing different here. For the boundary condition, integration by parts boundary conditions for one dimensional domain boundary is only x1 and x2. Whereas here, if I have area like this is my area over which I am integrating. Okay. So, here this is inside, this is the boundary, that is we denote it as dou A, that is the boundary. So, that is what we want to get out of this is still integrated over the area, we want to reduce it to the boundary, and that is where we use what is called Green's theorem. Okay. This green color may not be visible to you, but since it is Green theorem, actually it is named after a person and not the color green. Okay. But anyway, it is a Green's theorem, right. So, let us look at what that is. What it says is that if I have some area and I have a quantity that looks like this: dou q by dou x minus dou p by dou y over the area. This theorem says that is equivalent to doing over the boundary p dx plus q dy. Okay. That is what this says, right. Now, let us look at what we have. So, if we compare this quantity dou q by dou x, that is what we have. This is q, okay. This part is q, and then minus dou p by dou y is what we have here. So, minus of that will become p, alright. So, qp over the area dA. Now, we reduce it to something on the boundary. Okay. So, I have to write this is the boundary part over the boundary, like boundary condition, okay, which will become p dx, p again dou f by dou zx delta z, right. So, what you have is dou f by dou z sub x delta z, that is what we want. Delta z is arbitrary, we have and then p into dx, okay, plus we have q dy. The q is dou f by dou zy delta z, dou f by dou zy delta z dy, that should be equal to 0, because that is what the condition we had according to Green's theorem, which is this. We got a boundary condition that over the boundary of that region, again if this is A, this is our dou A, which is the boundary of region A. This is the boundary of 2D region A that we have. If this is the region, we have the boundary, and that is where the boundary condition says dou A, we have to go around the boundary like this. We go around the boundary, on that what should be 0 is this, that is dou f by dou zx dx and dou f by dou zy dy times delta z equal to 0. If delta z is 0, then there is no problem, integral is satisfied. That is the what we call essential boundary condition, meaning z is specified. If we go back to the plate problem, if w x y is our function, if the plate is clamped around the edge, there delta w, that is a variation of w, just like delta z is 0, that will be 0. So, then you are fine. If it is free, then this thing should be 0 on the boundary, dou f by dou zx dx and dou f by dou zy dy, and that is how we get the boundary condition. This will be the Neumann boundary condition or a natural boundary condition. Okay. So, we have derived both the differential equation, which is this, and the boundary condition, which is this. We have derived it for a 2D problem. Okay. So, now with one variable we are able to solve, and we saw some applications. In this lecture we also see how to solve the 2D problems, and 2D problems are, they are both in geometry and mechanics, they are also in structural design. Let us say I want to design a 2D plate, okay, where I want to determine a function that is a function of x and y, okay, I can get that, right. So, we can deal with 2 independent variables now, and we can also pose this problem for 3D. Okay. So, now let us take a problem, minimize j. Now, I will take a function, since independent variables may be x, y, z, let me take a function something like, let us say phi, which is a function of x, y and z, that is our design variable. Our integrand now will be over a 3D domain, or I will denote it as volume V. So, some V, when I put this thing, that means that it is 3D volume, the inside part of it is 3D volume, and that is V. If I show dou V, that is a boundary surface. This is the surface enclosing the volume, enclosing the volume V. Okay. So, here I can write my integrand in terms of phi and then phi sub x and phi sub y, phi sub z. What does it mean? It means that dou phi by dou x, phi is a function of x, y, z, and this is dou phi by dou y, and this is dou phi by dou z. If I want, which we did not discuss in 2D case, which you could as well, we can take the second derivatives also, phi x x. By that what we mean is dou square phi by dou x square, and then I can have y y, I can have z z, I can have x y, right, that will be dou square phi by dou x dou y, and then I can have y z, I can have z x, and then over the volume, right. I can have a general function in 3 independent variables. When I say dV here, what I really mean is dx, dy, dz, okay, dx, dy, dz we can have. So, 1, 2, 3 independent variables. How do we do? It is exactly the same way. First we take the variation of j with respect to the function phi equal to 0. Recalling our Gattu variation definition, we write it as dou f by dou phi into delta phi, the variation in phi, perturbation in phi, plus f by dou phi x into delta phi x, and then the rest of it. How many ever terms there are, we will do all that, and that will be dV over the volume is equal to 0. When we do that, so this implies this is already del phi, we do not do anything about, because del phi is arbitrary, right. That is what we use to get the differential equation and the boundary condition. Now, when you have things like this, we use the same trick that we used before, that is we replace that with something that involves only del phi and not del phi sub x. Okay. So, when we do all that, we collect all the terms that will have del phi, and that gives us the differential equation, and then del phi, which will be in the boundary part of it, like recalling again 2D, where we get something like this, where the del z was inside, we have to use Green's theorem. In the case of 3 dimensions, we have to use Gauss divergence theorem, that is the integration by parts equivalent in 3 dimensions, Gauss divergence theorem, okay, to get the boundary conditions, that is to get the boundary condition on the surface of the 3 dimensional volume. Again you see here, this is our dou V, surface enclosed in the volume V for a 3D problem, like a 3D elastic solid. You want to do work with that, there is a volume and there is a surface. So, surface will have the boundary condition, volume will be the interior. Okay. This is to get the boundary condition. Okay. Remember that integration by parts became Green's theorem for 2 dimensions and became Gauss divergence theorem for 3 dimensions, that was 2D Green, Gauss 3D, okay, and integration by parts for the 1 variable. That is how we get. In fact, if we were to do this, you can see in the accompanying slides of this lecture the detailed derivation of how it comes about. We have done it by hand step by step today for 2 dimensional case. You can also do it for the 3 dimensional case, where we will be able to look at the differential equation and the boundary conditions for the problem. So, we can solve in 3 dimensions, that means that independent variables will have x, y, z. In calculus of variations, one can go to more independent variables. We run out of symbols, but you can call it x1, x2, x3, x whatever p, but such problems are rare in engineering. In physics, quantum mechanics, sometimes people need to use more variables, but normally 3 are good enough for us. Time will also be a variable. So, if I go to dynamic problems, I can have phi a function of x, y, z and t. T is like a 4th variable. Most often you do not have to treat it like a 4th variable, things work out with just 3 variable, but one can do this. So, if you recall the generalization, we started out with only y of x, and then we went with y1, y2, yn, and then we had one derivative and several derivatives. Now, we have not just one independent variable, several independent variables. So, it will be nice if you look to the accompanying slides of these lectures and understand how we go from 2D to 3D. We will do some problems and then you can refer to the slides and understand both. Okay. In the next time we will do 2D and 3D, worked out examples to understand how differential equation comes up and how boundary conditions could be applied. Thank you.